Welcome back, Falcons, and we are moving into unit number 3, and it is all about how do we go about collecting data in AP statistics. So we're going to start off with chapter 11, and chapter 11 focuses on this idea of understanding randomness. So, as always, here's our homework problems from our book. They'll also be posted on Schoology for you to find. And if you want to think about this chapter in terms of its objectives, is we're using simulation to determine probabilities and experimental outcomes. So that is the first step in being able to run appropriate simulations for real world events. So just to encapsulate the power of randomness, if you were told that you had a chance to win a new car and you know the selection would be randomly made, would you feel the selection was fair? If you feel like it's fair, why in your gut, if I said that it's randomly selected, do you feel like it's fair to you? Or if you participate in a 50-50 lottery at a football game or a hockey game, that you feel like there's a chance for you to win. No one can influence or anticipate the selection. You being selected is just as likely as anyone else being selected. So the outcomes, or the winner, are equally likely. And that's the idea that it ties this idea, the randomness aspect together, is that if everything is equally likely, then we can start working with probabilities. Well, then it begs the question, what is random? So how do you determine if a series of events are random? So do you think that rolling a dice is random or rolling a die is random? Do you think that flipping a coin is random? Is starting the Super Bowl with a coin flip fair? Tails never fails, right? Do you think that test grades are random in comparison? So we call a phenomenon random if the individual outcomes are uncertain, but there is nonetheless a regular distribution of outcomes in a large number of repetitions. So if everything is equally likely, and we know that there is a set regular distribution, we can call that random. So of the numbers shown, choose your favorite number, 1, 2, 3, or 4. I want you to just pick a number, hold it up in the air. I know I can't see you, but if this was random, okay, 3, 2, 1, pick your favorite number. Now that you've chosen, write the choice in the chat. So in the chat, I want you to put this in the next time I see you guys. Do not change your choice. And if we had chosen at random, there would be an equal number of occurrences of each value. So we should be able to see, are there? So for statisticians, randomness is not some inconvenient lack of predictability, which a lot of people think, oh, that was just a random act. No, randomness is actually a significant concept for examining the world around us. It is the variability of events that provide interest and what we study. We want there to be randomness, like kind of we saw in least square regression models. We wanted that random scatter in the residual plot. That means it's worth looking at. So here's the rub. True random values are tough to come by. Computers, more likely your calculator, have become the predominant way to generate random numbers. The decimal values of pi can also be used as a random number table. Interesting. Computers do much better than people, but even computers rely on an algorithm and cannot truly generate random numbers. We call this pseudo-random. Using an algorithm to generate the random numbers we get from computers results in what are actually pseudo-random. Statisticians are good with that. Pseudo-random values are good enough for government work, and so we use it. So there are ways to generate random numbers so that all values are both equally likely and truly random. If we want to generate data that give a fair and reliable picture of the world, we use random numbers in simulations. So this is our key word for the whole chapter of real-world outcomes. We can then make predictions and draw conclusions using those random numbers. So here are some websites that generate lists of random numbers. You should care to use something other than your calculator. You can do random.org or randomizer.org or graphpad.com. We're going to stick with either the TI-84 or the TI-Nspire, and I will be demonstrating how to use the TI-Nspire in these videos. So with a simulation, The sequence of events we want to investigate is called a trial. The basic building block of a simulation is called a component of a trial. Trials usually involve several components going on at the same time. After the trial, we record what happened, and that is our response variable. That's our output. A simulation technique uses a probability experiment to mimic real life situation. So instead of actually doing the thing, we're going to use a random number generator to help us simulate what would have happened. Now, this idea is called the Monte Carlo method, and that's a simulation technique using random numbers. The random numbers can be generated by a computer or via a random number table. We will use the table so I can actually grade your efforts. And that's what the AP test is going to do. They're going to provide you with a random number table, and it's up to you to describe the techniques that you want to use. So here's the process of the Monte Carlo method. It is as follows. 1. List all the possible outcomes. Those are what we call components of the experiment. 2. Determine the probability of each outcome. Probability is the likelihood over the total number. And we'll get more into that, but the basic set of probability is if you flip a coin, one side is heads out of 2 total flips, so the probability is 1 out of 2. The probability that you pick a heart in a 52 deck of cards is 13 out of 52 or 1 out of 4 because there are 4 suits and you want to pick one of them. So we set up a correspondence between the outcomes of the experiment and the random numbers, or the numbers that we see, and these should be integers. We indicate when a trial ends. So how do we know that we have successfully completed that? Indicate what will be recorded. So what is the response variable that we're saying is happening? Select random numbers from a table and conduct the experiment. 7, repeat the experiment, which is a trial, and tally the outcomes. And then 8, compute any statistics and state the conclusion. So these are our 8 steps to run the Monte Carlo method. And it seems a little more complicated than it actually is, and it's pretty intuitive. So there are 2 basic forms of simulations. There's a fixed length trial. So a trial ends upon completion of a predetermined number of attempts. Think I want to pick 8 students at random. The number of successes is recorded. Here's another example. Shoot 10 free throws and record the number of made. So you can see that the components are made and miss, and we are running 10 total numbers and seeing how many makes and how many misses. 2, a variable length trial. So a trial ends upon completion of a predetermined number of successes, or the number of attempts is recorded, which is the response variable. So instead of shooting 10 free throws, we shoot free throws until 10 are made and record the number of attempts. So you can see that there are subtle distinctions between I want to shoot 10 or I want to make 10. So here is our first view of a random number table. So a small portion of a random number table looks like this. These are pages and pages and pages of computer printouts of random numbers. So columns and spaces are for ease of reading and are of no actual significance. So like this separation is just so your brain can comprehend the 5 numbers at a time. In the real world, when using the table, randomly select a starting value. So what do I mean by that? If we're going eeny, meeny, miny, start here, maybe we start here and then go every 2 values. What we could easily do is say, okay, trial number 2, I want to randomly start here and go every 2 values. You can see how randomly selecting it, there's an equally likelihood of where we start, so we can see an equal distribution of numbers that we get for our outcomes. So when using the table while taking a test, or the AP test specifically, we will start at the first value in the first row. So we will start in the upper left-hand corner. You do not get to make the decision about anything. Continue recording results without regard to row or column. Consider the random number table just one infinitely long continuous string of numbers. So there's no breaks, even though you see breaks. Just disregard those because those are helping you separate out these long strings of values. Okay, here's a simple example. Suppose you're interested in using a simulation to estimate the probability of flipping 2 coins and getting 2 heads. The component is flipping a coin. Each trial is flipping of 2 coins. So one way to do this is to let even digits, 2, 4, 6, 8, and 0, represent heads, and examine each pair of numbers to represent a trial of 2 flips. Separate pairs with lines indicating the end of a trial. So here we have 17 trials. We have 8, 1. So let's say, just as a reminder, even is heads. So what's the probability that we get 2 heads? Nope. Yep. 6 and 6? Yep. Nope. Nope. 6 and 0? Yep. 5 and 1? No. 3 and 0? No. 9 and 2? No. 9 and 7? No. 0, 0? Yes. 4, 1? No. 2, 7? No. 1, 2? No. 38? No. 2, 7? No. 6, 4? Yes. 9? No. So if we have 17, what I want to do is then figure out how many of these were successes. 3, 4, 5. In this simulation, what is the probability of getting 2 heads? 5 out of 17, which is actually pretty close to the theoretical probability of 1 out of 4. So you can see the usefulness in running simulations. Simulations is to experimental probability what limits are to theoretical probability. Theoretical is if we did this infinite number of times, what would we end up getting? How about another simulation? We can also use random digit table to estimate the probability of getting the sum of 7 using 2 die. Literally, what you can do is take a random list, let the digits 1 through 6 represent the number of dots on a die. We then skip the numbers 0, 7, 8, and 9. So if you get those numbers, it's impossible on a die, so we skip it. Again, we separate into pairs to indicate a trial. Pairs with 0, 7, 8, or 9 are eliminated. They're not possible. You can begin to see the problem with the random number table. I mean, there are options that we just have to omit. For example, 8, we don't use. That goes away. 4, 8 doesn't work. 6 and 6, okay, that is a thing, but that doesn't actually answer my question because the sum is not 7. 9 and 4, we can't use. 8 and 7, we can't use. 6 and 0, can't use. 5 and 1, okay, those work, but that doesn't add to 7. So 3 and 0, well, that doesn't work either. 9 and 2, nope. 9 and 7, no. 0 and 0, no. 4 and 1 works, but it doesn't work. 2 and 7, can't have a 7. 1 and 2, those values work, but that doesn't add up to 7. So you can see we're throwing out a lot of different options when we're looking through these numbers. So to determine the trials with a sum of 7. In this small setting, we have no successes. So we would need a much larger table to actually get a certain amount of 7s. And that's why you can see there's either a variable length or a set number of trials. If we just ran 10 of these, obviously we saw 0 successes. But we should understand that out of these options, it's probably like 7 out of 36 that we would get a sum of 7. Okay. Assigning numbers to components. The first step in a simulation is to identify the components. The second is to assign numbers to represent the components. And you must be careful when assigning numbers to outcomes. The number of digits assigned to an outcome must match the probability of that outcome. So you will want to use as few digits as possible when assigning numbers to outcomes. If possible, just stick with 0 to 9, that is 10 numbers. When the number of components is greater than 10, or the probabilities are not multiples of 10, you will have to use 2 digits, think 00 through 99. You must not mix 2-digit assignments with 1-digit assignment. So this is when we are listing out our components and the probabilities of each, then we are figuring out how many ways we can get this so it's equally likely, because the goal is equally likely. Okay, on your TI-84, when using a random number generator, you should seed the generator number to give you a unique random set. Now, on a TI-84, we'll type in a number. Some people usually type in their phone number. Then you hit store, math, probability, random, then enter. So once you do this, you seed the random number in so that the numbers you get out are actually random. Then to generate random numbers, we hit math, probability, random int, the minimum number, comma, the maximum number, and hit enter. To generate random integers in a list, do random int, min, max, and then give it a number of how many numbers you want, and it will actually give you a nice list. The newer TI-83 ACE will allow you to generate a list without repeats. Random int, no repeats. On a TI Inspire, if we switch over to our TI Inspire view, how do we get to random numbers? So here's just a normal calculator document. If I hit menu and I go to probability and I go to random, first thing that I want to show you is random seed. So I'm just going to type in a random number, 8675309. Phone number. It says done, so I've now seeded this calculator. You should only have to do this once. Now, what I can do is go to probability, random, and I can do random number and just hit enter, and it will give me a random number. If I take this and I want it to be between, let's say, 150, it gives me a random number between 0 and 150. If I go to menu, probability, random, and I go to integer, I can say, well, what integers do I want? Let's say I want from 0 to 99, and I want 5 numbers. If I hit enter, I get 52, 62, 58, 55, and 67. They give me 5 random integer values. If I just wanted to take this and delete lower number, higher number, hit enter, and I could just continue to repeat this every single time, and it's going to give me a random number. So you can see both the benefits of just typing in individually versus, let's say I wanted to do 10, I get my full list of 10. Once it gets larger than that string, we need to see it more in a spreadsheet, which is, if you wanted to, we can hit document, control document, and then we can go to lists and spreadsheet. Here, I can hit menu, data, random, and I want to do random integer. And let's say I wanted to do from 0, 99, 100 random numbers. 1, 2, 3, 4, 5, 6, 7, 8. You can see that once I type this into my spreadsheet, I get 100 random numbers in my table that I'm easily able to measure success or failure. Switching back to the notes, the next video, we'll go through a couple examples to see how you formulate a simulation. So hopefully you see the usefulness of each of these parts, and then we will move on to other ways of collecting data. So I'll see you in the next one, Falcons.